we have the equation y double prime plus 4y equals e to the t plus cosine 3t, and we want to solve the equation. We know we're going to have to find a characteristic solution and a particular solution, and we add the two. Now, we can plug in e to the lambda t, and we get roots of the characteristic equation that are 2i and negative 2i. And we're not going to explain that now. That's been done, and everybody seems to be good with that. Okay? And now we can just cut to the chase and say, well, we know this is going to give us a fundamental set cosine of 2t, sine of 2t. But let's go ahead and go through some of the constants and some of the rearrangements. I've left part of that undone because we just didn't want to take class time for it. Because you can always cut to this if you have to. But it's better to understand something about how this comes out of these complex solutions. So Euler's identity tells us that b e to the 2it is b times the cosine of 2t plus I sine of 2t. And c e to the negative 2it is c times the cosine of negative 2t plus I sine of negative 2t. Okay. Well, the cosine is an even function, as you should know if you understand the unit circle and how things give you the same results if you go around this way or around this way at equal distances. Or in terms of the behavior of the graph, it's clearly an even function if you know what a cosine graph looks like, and I certainly hope you do at this point in a differential equations course. The sine is an odd function, and that's equally easy to see from the graph. It's equally easy to see in the way the y-coordinates go if you move in opposite directions from the positive x-axis on the unit circle. So I'm not going to describe those things. We've talked about it, and I hope you understand those things because it makes it much easier to think about this. However, whether you do or not, we can then say that, okay, well, this is going to be a cosine of 2t, and this is also going to be a cosine of 2t since cosine is an even function. So we got b plus t times the cosine of 2t. And over here, we're going to have I times b sine of 2t plus c times the sine of negative 2t, but the sine of negative 2t is the negative sine of 2t. So we're going to have a minus c sine of 2t from this. We're going to have b minus c times the sine of 2t. Now, we can adjust our constants b and c, which are complex constants. They can be real, they can be imaginary. Okay? We can adjust those constants as we wish to get different types of solutions. So that's what we have left out here. I didn't want to go into that detail for purposes of time. But whatever b plus c is, that's going to be an a1 plus a2. Well, let's not do that. No. Whatever b plus c is and whatever b minus c is, and b plus c can be any complex number, and b minus c could be any complex number. This simplifies. And one general form we have is like a cosine of 2t plus phi. Okay, so I'm going to use that as the form that I want to use. Okay, so this can be put into the form a1 cosine 2t plus phi 1 plus I multiplied by a2 cosine of 2t plus phi 2. Okay, phi 1 and phi 2 will be different. But and a1 and a2 will generally be different. They don't have to be, but the phase angles do have to be, for reasons that you might want to think about. Okay, well, we've also established that the real part of this solution is a solution to the equation, and so is the imaginary part. So I choose the real part as my solution to this equation, and it's a1 cosine 2t plus phi 1, which I will subsequently, since I don't need to distinguish it from the a2 cosine of 2t plus phi 2 beyond this point, since I'm not going to talk about this anymore, I'm going to just write that as a cosine of 2t plus phi. I'll drop the subscripts. Now let's be clear. Another way we could write the general solution is a cosine of 2t, alpha cosine of 2t plus beta sine of 2t. I'm running out of letters here. We can put this into this form just by our most basic trigonometric identities for double angles and so forth. And it's quite straightforward to do so, and I certainly hope you have by now, because you're to the point where you need to be able to do that. I've been warning you about it for quite a while. So this is directly related to this form of the fundamental set, and this is equivalent because this can be put in the form of this, and this is the form I want to use right now, because it's a little simpler to manipulate. No reason you couldn't do it with this, but you'd probably like this better. All right, now, this is our general solution to the homogeneous equation. We can get two linearly independent solutions by just using two different numbers for our phase angle. Okay? If our phase angles aren't the same, the functions are linearly independent. Just as the sine and cosine are 90 degrees out of phase, well, as long as these are some number of degrees out of phase, you choose two of these, choose two different constants, two different values of your phase angle, it's going to give you linearly independent solutions, and that would be to your benefit if you're halfway interested to try to prove that. It's not difficult. But you're not used to proving things, so it could be challenging. Okay, now, we want to talk about a particular solution, but the camera's been misbehaving a little bit. I think I've got it fixed. So I'm going to stop this video and pick that up in the next, because I'm afraid I'm going to run over anyway.